What's going on, guys? I want to sort of make this video about a new book that I just read. It's sort of about the scaling era of this time, and it recently came out. It's by Dwarkesh Patel and Gavin Leach, and I wanted to take you through the book and the core argument because I think it's one of the most important things you could be paying attention to right now. The basic premise is we're living through one of the most consequential periods in technological history, and most people don't realize it. The thing is, it doesn't feel like a revolution because it's basically happening incrementally. Every few months, there's a new model. It's a little better. People get used to it, and then there's another one. So let me break down what this book is actually saying, and I will link the book in the description below. Here's the central thesis, and it's deceptively simple. If you make AI models bigger, more parameters, more training data, more compute, they get smarter. And this relationship is weirdly predictable. It follows what researchers call scaling laws. Now, I know that sounds obvious. Of course, bigger is better, right? But what's remarkable is how predictable it is. We're not talking about vague trends. We're talking about mathematical curves that have held up across multiple orders of magnitude. OpenAI took a $4 million risk training GPT-3 because they could see from smaller experiments roughly what they were going to get. And they were right. In other words, the compute used to train a leading model today is about 10 billion times higher than it was in 2010. Let me say that again, 10 billion times. If the compute for a 2010 model was a laptop, the compute for Gemini Ultra would cover the area of New York City. The trend line has been doubling every 6 months. That's 4 times faster than Moore's law. And this scaling hypothesis, which Gordon Branwin coined in 2020, is the idea that this exponential investment is all we need to build human-level AI, maybe even systems that surpass human intelligence. It's not a guarantee, but it's also not crazy. The trend lines have just kept holding. Here's the uncomfortable part. We still don't fully understand why scaling works. Dario Amodei, CEO of Anthropic, says it in the book pretty directly. The truth is that we still don't know. It's almost entirely just a contingent empirical fact. There are hand-wavy explanations. Jared Kaplan, one of Anthropic's co-founders, suggests you can think of neural networks as fitting a multidimensional curve to a data manifold. As you add more parameters, you're essentially cutting your data into finer and finer pieces. More resolution, better predictions. But here's what's strange. You can predict the loss, the statistical average of how well the model predicts the next token, sometimes to several significant figures. That's the kind of precision you see in physics, not in messy empirical fields. Meanwhile, specific capabilities, when a model will learn arithmetic or start to code well, are incredibly hard to predict. Those often emerge abruptly. Ilya Sutskever, co-founder of OpenAI and now Safe Superintelligence, puts it almost mystically. The models just want to learn. You have to understand this. The models just want to learn. It's a bit like a Zen koan. You listen to it, and either you get it or you don't. Now, if scaling is the game, what does it actually take to play? 3 things: chips, power, and data. Let me walk through each. Chips. For the past few years, there's been an insane scramble for GPUs, specifically NVIDIA's H100s. Companies couldn't get enough of them even if they had the money. The constraint has loosened somewhat, but the demand is still astronomical. Leopold Aschenbrenner, who runs an AI-focused investment firm, lays out the trajectory. GPT-4 trained on about 25,000 A100s. By 2026, we're looking at clusters of 1 million H100 equivalents. By 2028, 10 million. By 2030, maybe 100 million. Power. And here's where it gets wild. A cluster of 1 million GPUs doesn't just need chips, it needs electricity, a lot of it. We're talking gigawatts. For context, 1 gigawatt is the output of a large nuclear reactor. The Hoover Dam produces about that much. Mark Zuckerberg says in the book that nobody has built a 1 gigawatt data center yet. I think it will happen. It's only a matter of time, but it's not going to be next year. Dylan Patel, chief analyst at SemiAnalysis, thinks we'll see 1 gigawatt clusters by 2026. By 2030, some projections suggest 100 gigawatts, over 20% of current US electricity production going just to AI. That's not a typo. Data. The third input is training data. Llama 3.1 was trained on 15 trillion tokens of text. There's a real concern that we're running out of high-quality human-generated text on the internet. The solution, synthetic data, having models generate their own training data, or multimodal training using images, video, audio. But these approaches have their own challenges. Okay, so let's assume the scaling hypothesis is roughly correct. What does that actually mean? It means we might be building systems that can automate most cognitive labor within the next 10 to 15 years. Not just writing code or answering emails, which they can already do reasonably well, but doing scientific research, making strategic decisions, designing new technologies. Carl Schulman, an independent researcher who advises open philanthropy, puts it starkly. If you automate human labor, we currently have a $100 trillion economy. And most of that is paid out in wages, between $50 and $70 trillion per year. If you create AGI, it's going to automate all of that. That's the upside case. The downside case is also in this book, and it's not pretty. Here's the thing about building extremely capable AI systems. You have to make sure they actually do what you want. This is called the alignment problem, and it's arguably the hardest unsolved problem in the field. Eliezer Yudkowsky, who's been warning about AI risks since the early 2000s, is pretty pessimistic. He compares alignment research to trying to design a rocket while you don't understand physics well enough to know if it will blow up on launch. His take, if your entire alignment proposal is an elaborate mechanism, if you can't say, here's the core alignment problem and here's the key insight that addresses it, then I can tell it's not the right way. But other researchers are more optimistic. Ilya Sutskever thinks we can combine multiple approaches: adversarial testing to find mismatches between desired and actual behavior, interpretability research to understand what's happening inside the neural net, and continuous improvement where alignment keeps pace with capability. The book includes a fascinating exchange where Joe Carlsmith, a philosopher at Open Philanthropy, draws an uncomfortable parallel between alignment and authoritarianism. Mao's 100 Flowers campaign let people criticize the regime, and then purged everyone who did. Is that what we're doing when we test whether a model will defect given the chance? It's a disturbing question. That's the upside case. The downside case is also in this book, and it's not pretty. Leopold Aschenbrenner makes a strong case that the trillion-dollar clusters being planned for 2028 to 2030 need to be built in the United States or allied democracies, not in the Middle East, not anywhere with weird ties to China. His reasoning, these clusters might be the superintelligence clusters. If you build them in an authoritarian dictatorship, they can exfiltrate the weights, they can seize the compute, they get seats at the AGI table. Would you do the Manhattan Project in the UAE? He asks. Probably not. So when does all this happen? When do we get AGI? The book surveys a range of estimates, and they're all over the map. But Patel himself puts his probability of AGI by 2040 at about 60%. That's not a prediction. It's an estimate with massive uncertainty bars. But it's not negligible. The key uncertainties he identifies are: can we maintain exponential increases in inputs? Specifically, can models learn to evaluate their own output and generate useful synthetic training data? Will LLMs ever generalize like humans do? Humans learn from much less data. We have flashes of insight. Can models compensate with sheer scale? Or is there something fundamentally missing? Will algorithmic improvements keep stacking? If they don't, the fast takeoff scenarios where a sufficiently advanced model bootstraps itself to superintelligence become much less plausible. Look, I really can't say much about how this will play out. Nobody can. But I think the framework here is valuable. The question isn't, will AI be a big deal? The question is, given that scaling has worked so far, and given that massive resources are being deployed to push it further, what happens next? If the scaling hypothesis is wrong, if there's some fundamental ceiling we're about to hit, then we're probably looking at a useful but limited technology, an extremely capable autocomplete. That's the bear case. If the scaling hypothesis is right, even partially, we're looking at something much bigger, something that might automate cognitive labor at a scale that transforms the global economy, something that might help us solve problems we couldn't otherwise solve, or something that might pose risks we've never faced before. And the thing is, we're going to find out pretty soon. The experiments are already running. The compute is already being deployed. The next few years will tell us a lot.